All right, it is 7.3. So this is proving a quadrilateral is a parallelogram. So last time we did stuff that we were given quadrilaterals and then given properties of them. Looking at 7.5. This time we're kind of doing the opposite. We're given properties, and then that determines if it is a quadrilateral / parallelogram or whatever. So we're doing the converse of basically 7.2. So keep that in mind as we go forward. So everything in 7.3 is kind of the converse, the opposite of what we do in 7.2. Everything we do here proves something is a parallelogram. I don't think I wrote this right in the notes. Because everything is going to say, because it's a parallelogram. It's a parallelogram. I did not print out the notes right. Anyways, besides that point, let's get started. 7.7 theorem. Parallelogram, opposite sides, converse. If both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Get used to writing that one out. So this is the converse to theorem 7.3. And it states that if we have a D congruent to BC, and if we have a B congruent to CD, then ABCD is a parallelogram. Simple enough. All right, 7.8. Parallelogram, opposite angles, converse. If both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Then. This is a converse to theorem 7.4. So that means if we have angle B is congruent to angle D and angle A is congruent to angle C, then ABCD is a parallelogram. This unit, or this section, bears a striking resemblance to 3.2 and 3.3, where we have to do converses. Remember that the converse statements that we're making right now is what can prove something to be a parallelogram. Keep that in mind. We'll be doing some examples. In example 1, we are given a quadrilateral ABCD and given some facts like ABCD is equal to BC. We're given that AB is equal to BC and CD is equal to DA. Is ABCD a parallelogram? Well, let's find out. First off, draw it out. I need to use a different color. Too much blue. Say this is A, B, C, and D. And we're given that AB is equal to CD, so I'm going to give them a mark right there. And I am also given that CD is equal to DA. Is this a parallelogram? No! No, it is not. It doesn't follow any of our rules. The converse we should be looking at, or the theorem, is 7.7. none of these sides are congruent to each other. No opposite sides are congruent to each other. We would want that AB is congruent to DC, but we don't have that. We have AB is congruent to CB, and DA is congruent to DC. So, is ABCD a parallelogram? No. ABCD isn't a parallelogram. No opposite sides are congruent. There you go. And example 2. What values are x and y in the quadrilateral of a parallelogram of STUV? Yeah. This is kind of just like what we did last time. Knowing the opposite sides are congruent because it's already stated that this is a parallelogram. Stated right here, parallelogram. Opposite sides are congruent, so I can find my x's and y's easily. Notice that ST and VU, they both have x variables. TU and SV, we have an x and a y, so it'd be more nice to go with the horizontal ones, or the lines that go vertical. So let's put 24x is equal to x plus 6. We're going to go with those two pairings first, because I think that's going to be the easiest one to solve for x, or just get started, to be honest. Move x to the other side. I'm having a brain fog right now. 24 is equal to 2x plus 6. Get that 6 away from me. And then I should end up with 18 is equal to 2x. Divided by 2, x is equal to 9. We even on screen? We are. Red. Alright, so I'm given that x is equal to 9 now. I'm going to take that and plug it into this up here. So I'll have 2x plus 3 is equal to y. Take that 9, I'm going to plug it in. So I have 2 times 9 plus 3 is equal to y, which will give me 18 plus 3 is equal to y, which is 21. So your x should be 9 and 21 should be y. Not too bad, is it? But what's bad is that we have 2 more theorems. I'm just kidding. They're not bad. Just joshing you. All right. Opposite sides parallel congruent theorem. Ooh, different. In one pair of opposites of a quadrilateral are congruent and parallel, then the quadrilateral is a parallelogram. You guys are lucky. I would have made you guys write so much more different stuff if I actually made sure I copied my notes right. I could just make you guys all write this on paper, actually. Make you guys suffer. Yeah. Anyways, what does this mean? So if I have that BC is parallel to AD, if I have opposite sides that are parallel with each other, I colored in the wrong part. So I have the arrows, these mean parallel. If I have 2 parts that are parallel and those same parts are congruent, then ABCD is a parallelogram. So I guess note that both parallel and congruency are required. Now it's this one. Okay, it is on screen. And this does not, there's no converse to this one. But there is a converse for this one. Or at least like a theorem that we learned before. Theorem 7.10, parallel diagonals converse. If the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. Get excited. This is a converse to theorem. Oh, what? Oh crap! What is it? Hold on. Converse to theorem 7.6. The one in 7.2 where we dealt with diagonals. This is the converse to it. So, if we're given that BD, segment BD and segment AC bisect each other, then ABCD is a quadrilateral. Woo! All right. Use the photo to show you how to what? Use the photo to shoe. Oh my god. No. No, not shoe. To show how you know angle S is congruent to angle V. Angle S is the... Oh, it doesn't even show up. This picture doesn't do it justice to, like, actually see what's going on in the figure, so I'm going to actually draw it out. I think drawing it out will just kind of show, like, hey, this is what's happening in the picture. So we have S, T, U, and V. One thing that I noticed already in the picture is that we have segment ST is not only congruent to segment VU, but it is also parallel with VU. So by that, by theorem 7.9, STUV is a parallelogram. And since we know STUV is a parallelogram, that means angle S is going to be congruent to angle V, not VU, because of theorem 7.4, the opposite angles theorem. There we go. Kind of a makeshift proof if you want to think of it that way. At least that's how I kind of did it. Whatever. Example 4. For what value of x is the quadrilateral CDEF a parallelogram? All right. So how can I picture this one and justify something? We have congruent marks right here. We have two lines that are bisecting each other. Why do I say they're bisecting? Is because one, they're crossing each other, and two, we have that FD is split into two congruent parts, going from FN and ND. Looking back up top to theorem 7.10, the parallelogram diagonals converse. We have two sets of congruent marks. So that means I can put a set of congruent marks on here as well. So CN is congruent to NE, which also houses 4x minus 11 and 2x plus 17. I can set them equal to each other and find x. So I'll have 4x minus 11 is equal to 2x plus 17. And now I can solve for x. Get that 2x to the other side. So we'll have 2x minus 11 is equal to 17 plus 11. 2x is equal to 28. Divide by 2, x shall equal 14. Not too bad. Last one. Show that quadrilateral ABCD is a parallelogram. How are we going to do this? How? Well, there's many ways. Many different ways that we could do this. I'll even write many ways to do this. And we shall be doing a couple different ways. Luckily, I'm doing this on Friday, where I will be gone, so you have to do it all. One way that we can do this is by opposite sides being congruent to each other. Opposites congruent. Sides. I should get more colors. We could do the same thing with opposite sides being parallel with each other. I'll just keep it open. Just keep the pens open. Number 3. Another way we could do that is that we have one pair of opposite sides, both congruent and parallel. And one more. What color am I going to pick? I'm going to say it is pink. I chose an electronic pen from my cup. Yellow. Oh, God. Oh, no. You guys are not getting yellow. I gotta look. All right, we get orange. And then diagonals bisect. All right, so you see this, and it's like, okay, cool. Now, how am I actually going to do this on the problem? Well, we have our friends, the distance formula. Remember then? Yep, you do. That's not how you spell formula. Y2 minus Y1 squared plus X2 minus X1 squared. And the slope formula. We don't need a square root for the slope formula. All right. We can use these two formulas to go through these. Like with the green, we can use distance formula. So opposite sides congruent. For opposite sides parallel with each other, we can use the slope formula. For diagonals, we can use the distance formula. And I don't want to do the red one. For 3, you would have to do a combination of both. So let's just go through it. Let's go. Yeah, I'm gonna do 2 of them. Let's do green. I'm gonna prove it's a parallelogram this way. So we're going to be doing the distance formula for each one. I need to find sides that are congruent to each other. More specifically, I want to see like this side, like I want to see this. So I want AD to be congruent to BC and BA being congruent to CD. That's what I'm trying to see. Let's get working. So AB, our distance formula is going to be -2 minus 0 squared plus -2 minus 0 squared. All under that square root, we'll end up with 4 plus 4, and that's going to be equal to 8, still under the square root. I get the 4s because I skipped a step. You end up with -2 squared plus -2 squared. That's how I got the 4s. I skipped it. All right. CD is next. Let's see if we get -8. The square root of 8. -4 plus, -4 minus -2 squared plus 2 minus 4 squared. Now I can plus it because subtracting a negative gives me a positive. So I would end up with a -2 squared plus a -2 squared, giving me a 4 plus 4, which is a square root of 8. Congruent sides. And then I can do BC. Gotta do my other set. So I will have -4 minus -2 squared plus a 2 minus -2 squared. You change all these to positive since I'm subtracting a negative. And then I shall end up with a -2 squared plus a 4 squared, giving me 4 plus 16, and that's the square root of 20. BD, the last one. 4 minus 0 squared plus -2 minus 0 squared, giving me a 4 squared plus a -2 squared. That's 16 plus 4, and that is the square root of 20. Congruent sides. ABCD is a parallelogram. There we go. The 3 dots is there for. A little bit of a task, one would say, for this. Alrighty. Let's do opposite sides. Well, the blue. So, they're all opposite sides. Let's do the parallel ones. The parallel, we can do the slope formula or we can count. Either way works in our favor. So I'm going to do that. And let's start finding slopes. I have AB. I want AB to have the same slope as CD. So these need to be parallel with each other. And then these need to be parallel with each other. BC and DA. They're not in the same spot. Oh, well. All right, AB. I'm going to count. That's just going to make it easier. And it's less writing that I have to do. You could do the actual formula for it, but I don't want to. So let's start counting. Remember rise over run. Over run. That's up versus across. So 1, 2, 1, 2. So we rose 2 over 2. That's going to give me a slope of 1. CD. We're going to go up 1, 2, 1, 2. We rose 2, went over 2, gives me a slope of 1. Parallel sides. All right, let's do the same thing. We're going to go from A to D. 1, 2, 3, 4. I went across 4, so that's my bottom. And then 1, 2. I went down 2, so that's -2. So I went down 2 across 4, giving me a -1/2 slope. And then CB. I wrote it wrong. We're going to go down 1, 2, and then 1, 2, 3, 4 across. So down 2, 4 across. That's 1/2, and that is parallel side still. And that means, therefore, ABCD is a parallelogram. I'm going to be honest, I feel like one of these two are going to be your easiest friend while doing this. I say the slope one is probably going to be the quickest way to doing it. So the blue one, the one I saved for last. I did not think this would be such a long video, but it is. Oh my god. Anyways, I'm at MSU. I will see you on Monday. Your homework assignment isn't too bad. So have fun. That's due on Monday. We'll go over it on Monday.